So in the final video on discrete time Markov chains, I'll consider rewards and expected reachability for our DTMCs. So here we're going to augment our DTMC with rewards, or conversely costs. So these are real valued quantities that we assign to either the states or our transitions of our DTMC. And these can have a wide range of different interpretations. So just to give you some examples, we can use them to represent the elapsed time, power, our consumption. So this can either correspond to the power that we consume in a state, or the power that is consumed when we make a transition. We can use it to find out the size of our message queue. We can count the number of messages that we've successfully sent. We can measure the profit, and there's many other examples. So I will call them rewards, but they can also have a negative interpretation as costs. Mathematically, it doesn't make any difference, but you would think that if it was costs, then you'd be trying to minimize them, while you'd be trying to maximize rewards. So let's formally define what it is to give a DTMC a reward structure. So we have both a state reward function. So this given some state, it will return a real valued it'll return a real value. And we also have a transition reward function that, given any pair of states, gives a real value, which is the reward accumulated when we perform that transition. So just to give some concrete example, if we wanted a reward structure for time steps, then the state reward function wouldn't be used, and R would give the real value 1 for every transition. If we wanted a reward structure for the number of lost messages, then we would return 1 for every transition which corresponded to losing a message. For power consumption that I've already mentioned, then the state reward function will be used to define the per time step energy consumption in each state, and the transition reward function would be used as the cost of each, the energy cost of each transition. So we need some more probability basics. So let's go back to there. So if you recall, a probability space is a tuple where we've got a sample space, and then we've got the event set, and then we've got a probability measure, which, given any event, gives the probability of that event. So if we have a real valued variable over the probability space, so this is a function that, given a element element of sample space, this returns a real value. Then we can consider the expected or average value of the random variable. So this is given by, we take a integral over all elements of the sample space, and then it's with respect to the probability measure. So if we've got a finite or our discrete probability space, then we can turn this into a sum, which is just the sum of the values multiplied by the probability of them. So let's give a concrete example. So here we've got the expected or average value of a die when it's tossed. So what's the probability space? Well, this is the possible value. So either it's 1, 2, 3, 4, 5, or 6. And the events are just all the possible subsets of the sample space. And we know that the probability of throwing a 1, 2, 3, 4, 5, or 6 each has equal probability of 1, 6. So the random variable here will, if we throw a 1, what's its value? Well, that's obviously 1, and then so on for 2, 3, up to 6. So what's the expected value? Well, it's just the sum of the probabilities multiplied by other values. So this gives us that the expected value is actually 3 1/3. So let's now go on to expected rewards for DTMCs. So we've got, if you recall, the sample space for the probability space for our DTMCs, it's the sample space is the set of infinite paths. So therefore we want random variables which are of the form, they take a infinite path and they return a real value. So if we consider any infinite path, then one such reward, one such random variable can be the reward accumulated before we reach some target set T. So here it's the random variable X. So first we must find the first time that a state T is reached, and then it is the sum of both the state and the transition rewards before we reach T for the first time. However, if we never reach the state T, then we just set the cumulative reward to be infinity. So what I'm now going to show you is how we can compute this using graph-based analysis and solving a system of linear equations. So here let y(s) denote the expected value when we start from state S. Now, if we're already in the target, then there is no rewards to accumulate, so we can set y of s equal to 0. If s doesn't reach the target with probability 1, then we can set it equal to infinity. And this just, if we have just one path that doesn't reach the target, then this path will have the value infinity, and therefore the sum will have the value infinity. And for other states, we do it are recursively, similar to the case of probabilistic reachability. So it's from state S, it's the state reward associated with S plus the average or expected transition reward when we leave state S, and then it's the average of the expectations of all the successor states. So let's see this in our practice. So let's go back to our simple example of modeling a die with a fair coin, and here we want to know what's the expected number of coin flips until we reach a done state, or a state where we know the value of the die. Okay, so this is the expected number of coin flips or steps. So we'll associate a reward of 1 with each transition, and we won't have any state of rewards. So for all of other target states, then we set the value ys to be 0. All of the states reach the target set with probability 1, so we don't set any equal to infinity. And then for the remaining states, well, let's first look at s 0. So here we've got the sum, so there's no state or reward, and then there's it's the average or of the transition reward. So it's 1/2 times 1 plus 1/2 times 1, and then we've got 1/2 times the expected reward for S1 plus 1/2 times the expected reward of S2. Okay, and then we can simplify that to this form given here. And if we keep going, I can also show you state S6. So we get the same thing that we sum over our transition our rewards, and then here it would be 1/2 multiplied by 0, as this is in our target set, plus 1/2 times y of S2. And if we keep first simplify, then we can substitute these two values into the other equations. We can simplify again, and then finally we can substitute these values into S0, S3, and S6, and we find out that y of S0 is 11/3. So the expected number of coin flips before we know the value of the die is 11/3. So just to mention our complexity here. So here, similarly to probabilistic reachability, it reduces to first graph-based analysis. So here, we have to find the set of states that reach the target with probability 1, and then we have to solve a system of linear equations. For the graph-based, this is linear in the size of our DTMC, and then we need to solve a system of linear equations. And as for probabilistic reachability, this is polynomial or cubic in the size of the DTMC. And again, in our practice, we would actually use iterative methods as opposed to solving a system of linear equations. And as for probabilistic reachability, we can express this computation as a least fixed point. So finally, I'll mention there are additional reward properties. For example, we can consider instantaneous reward properties. So these can ask, what's the expected value of a state reward at a given time step? So for example, what's the expected queue size after 90 seconds or 90 steps? Or there's also the cumulative time bound properties. For example, what's the expected cumulative reward up until time step k? There's also, for those that are interested. There's long run, average, and we can have multi-objective properties that include rewards. So that finishes this set of this part of the videos, and in the next set I will go on to markup decision processes that extend DTMCs to allow the modeling of non-deterministic behavior.